Okay, so you've seen robots in movies, you've seen them online, but have you ever really thought about what it takes to bring one to life? I'm not just talking about code on a screen. I mean a real physical robot that can walk, see, and actually think for itself. Well, that's exactly what we're diving into today, a builder's guide to physical AI. Let's get into it.
It really all boils down to this one huge question. How do you give a robot a mind? I mean, think about it. It's not just about nuts and bolts, right? It's about creating something that can perceive the world, understand it, and act on that understanding. So, where do you even begin to build something like that, an artificial consciousness? The answer, the key to all of this, is something we call physical AI. The best way to picture it is like a bridge. On one side, you have the pure digital brain of an AI, and on the other, you have its physical body. Physical AI is that bridge that connects them. And the guide we're walking through, it's basically the blueprint for building that exact bridge, piece by piece.
All right, every great build has to start somewhere. For us, it's right here. We're starting with what you can think of as the robot's nervous system. It makes sense, right? Before it can think, before it can move an inch, it needs a way for all its parts to talk to each other. It needs that communication backbone.
And that backbone? It's built on a system called ROS2, which stands for Robot Operating System. And honestly, the central nervous system analogy is perfect. It's this incredible open-source framework that basically lets everything, the cameras, the arms, the brain, all communicate instantly. It's the industry standard for a reason. That common language is what makes everything else possible.
So your first quest, if you will, is to get a handle on a ROS2. And it breaks down into these 4 key steps. First, you got to learn the core architecture, the big picture. Then you get into the nitty-gritty, nodes and topics. Just think of nodes as tiny little programs for each part, like one for the camera, one for a wheel, and topics are the mail routes they use to send messages to each other. Simple, right? After you set up your environment, you're ready to get them all talking. You absolutely have to nail this stuff, because it's the foundation for literally everything else.
Okay, so the nervous system is in place. You might think the next step is to grab a screwdriver, but not quite. This is where things get really cool. Before you build a single physical part, you build its digital twin, a perfect replica that lives inside a computer simulation.
And I know what you're probably thinking. Why? Why bother with a virtual robot? If we want a real one, why are we playing a video game first? Well, the answer is pretty simple. It's smarter, safer, and way, way cheaper. The simulation is your sandbox, your playground. It's a place where you can try out crazy ideas, push your robot to its limits, let it fall over 1,000,000 times, and it doesn't cost you a dime in broken parts. This is where you nail down the super important skill of sim-to-real transfer, getting what works in the virtual world to work in the real one.
And to build this virtual world, you're going to lean on 2 main tools. You've got Gazebo, which is like your physics engine. It makes sure that when your robot drops something, it actually falls, It handles gravity, friction, all the real-world rules. And then you have Unity, which is for making the world look real. It lets you build these beautiful, complex virtual environments for your robot to live in.
All right, this is it. We have a nervous system. We have a body, a virtual one at least. Now it's time for the best part, giving it a brain. This is where we go from a simple machine to an intelligent being, using some seriously powerful AI tools like NVIDIA Isaac.
So, first thing that an intelligent brain needs to do is see. That's computer vision. And let's be clear, this is so much more than just having a camera. A camera just records pixels. Computer vision is about teaching the robot to understand those pixels, to know that this cluster of pixels is a chair, and that one is a person. It's about giving sight meaning.
Next up is sensor fusion. Think about how you experience the world. You see things, you hear things, you feel things, and your brain just seamlessly combines it all into one single reality. That's exactly what sensor fusion does for a robot. It takes data from its cameras, its depth sensors, all its inputs, and fuses it together into one coherent picture of what's going on around it.
Okay, so now the robot can see and understand its environment. Great. But how does it move through it without bumping into everything? That's where motion planning comes in. It's like the robot's own internal super GPS. It doesn't just know the destination. It's constantly calculating the most efficient, safest path to get there, planning every single movement.
And finally, we get to manipulation and grasping. This is where the rubber really meets the road. It's one thing to see a coffee cup. It's another thing entirely to pick it up without crushing it. This is how the robot learns to interact with the world, how to hold things, how to use tools. This is where all that digital intelligence turns into actual, physical, useful work.
So this is the moment we've been building towards. We've got all the pieces of the puzzle laid out. The nervous system, the virtual body, the powerful AI brain. Now, we put them all together. We connect its vision, its ability to understand language, and its power to act. It's time to bring this thing to life.
And just look at what happens when you connect all those dots. You can give it a simple command, something like, "Hey, can you grab my water bottle from the table?" And the robot just does it. It hears you, it uses its vision to find the bottle, it plans a path to the table, and it uses its grasping skills to pick it up. All of that knowledge from the simulation, plus its safety rules, all working in concert. It's incredible.
And after going through all of that, something fundamental changes. You're not just a student reading a manual anymore. You've made the leap from learner to builder. You have the skills, and now you're ready for the final exam.
And what's the final exam? It's the capstone project, building one fully autonomous humanoid robot. This isn't just one more lesson. No, this is the final boss. It's the one big challenge where you have to pull together every single thing you've learned to make it work.
I mean, listen to how the guide itself describes it. A comprehensive capstone project integrating all concepts. That really says it all, doesn't it? This isn't about just one skill. It's the grand synthesis, pulling everything from the low-level ROS2 communication all the way up to that high-level AI brain into one single working creation.
And once you pull that off, you'll walk away with a toolkit that honestly feels like a set of superpowers. You'll have mastered ROS2 for controlling robots. You'll be an expert in simulation. You'll have real skills in computer vision, motion planning, and manipulation. You'll basically understand the entire pipeline for creating an intelligent physical machine.
So here's the real takeaway. The future of AI isn't some abstract thing living on a server somewhere. It's going to be embodied. It's going to be all around us, in the physical world. And that future needs to be built. So, the only real question left is, are you ready to build it?